Desktop. Screen. Can you all see my share screen?
Yes, sir. Can see.
Can okay. So, okay. All right. So we are moving to the last chapter already, which is the AC to DC converter. All right. So this is the most, I think, fundamental, all right, converter you all have learned in your analog, okay, when we will first learn about the diode, all right. So the first application, right, I believe we'll be introducing to you is the rectifier, okay. So that is the very first for most fundamental types of what we call the power electronics converter, which will change the AC to DC because our electrical grid, okay, AC, okay, simply because AC can transmission much more efficient compared to DC in terms of long distance, all right. And however, and our what we call appliances, okay, especially those electronics one, they are mostly DC. Okay, therefore we will require to have a AC to DC converter. So it is basically done by rectifier, okay, which consists of a semiconductor diode, okay, thyristor, or this transistor. So we will look into all these different variations. And then, of course, as we know that, all right, when we perform the AC to DC converter, the conversion, you will never get an ideal DC. Okay, you will have some form of ripple. Of course, that can be so small until it can be neglected. Okay, but just bear in mind that they will have some form of variations. Okay, we call it ripples. Okay. All right. Now let's look back in time. Okay, in the old days. Okay, how do they actually perform this AC to DC conversion? Okay, back then there's no diode, right? Diode and transistor are invented in the 50s. Okay, in the 1950s, okay, right after World War II. So before that, right, we already have electricities, right? So for example, like in the year of 1888, okay, how do they do the conversion? Okay, the thing is that, okay, one thing when Edison, right, start to sell his light bulb, right, it's all powered by DC. Okay, it's all powered by DC. And his first proposed what we call electricity distribution, it is also DC. Okay, it's also DC. Of course, after Nikola Tesla has proposed the three-phase system, okay, so that it can, you know, transmit the AC power much more efficient compared to DC. But when you come to the end point, okay, or the distribution customer point, still you need to convert back, okay, to DC. Of course, it's not at every houses, but at their substations. So what they did is that basically they actually need to couple, okay, couple the AC motor that is coupled to the DC motor. Okay, for example, okay, like this one, you can see that this is one of the generator. Okay, and there is one of the motor. It's supposedly just a couple lah. It's used to see two set. So meaning that they will have a what we call AC induction motor, okay, where the power come in AC, right? When they want to convert it to DC, so this is connected to a DC machine. Okay, so it's mechanically coupled. All right, so the moving shaft, right, is actually mechanically coupled so that the rotation, okay, will convert it to DC. This is the very old days of AC to DC, okay, converters. No semiconductor, no diode, no switching, okay, involved. Okay, they simply just make use of two types of different machine to do the conversion. So this is a very first type of what we call the AC to DC conversion. That's been, it has been long, okay, you know, among the four types of power electronic converter, right? We have the AC, DC, all this, right? In fact, the AC, DC was the first, okay, converter, okay, but not in the form of power electronics. And then as time moved on, okay, into the earliest 90s, all right, you know, they no longer use the mechanical, because mechanical, they have a lot of losses. The power loss a lot because, yeah, you know, there are already losses from AC to, I mean, electrical to mechanical power, right? And mechanical power back to electrical power. So the losses are high, okay? The losses are high. So in order to solve that, of course, they need to find out ways. Of course, the next one will be using rectifier. Okay, the problem is that they do not have, again, semiconductor diode, right? In the 1901, you know, at the time when airplane still not yet invented. But they already invented something called mercury arc valve. Okay, so mercury arc valve, okay, it works like, I mean, the behavior of this mercury arc valve, it works like diode. So current will conduct in one direction, okay, but block in another direction. So of course, the valve inside is a vacuum valve, okay, a vacuum valve with the mercury, right? So when they are, and it works in high power, of course. So when they turn it on, like you can see, it looks like a light bulb, but this is all the electrical plasma, all right, that actually, you know, the electrical plasma, okay, that will light up. Okay, so these are the old days of rectifiers, okay, before we have invented the semiconductor diode. And of course, slowly they have make it smaller, okay. It looks like light bulb, so these are what we call the thermonic valve. Okay, so it's a old version of the transistor. Okay, the old version of the transistor, basically it consists of one cathode and anode. So no more mercury is using, and you don't see any plasma anymore, because this one, yeah, mercury is very poison. Okay, consider very rare types of elements, and then see plasma and huge in size. And of course they make it smaller like a light bulb. Okay, so it works like in the, what we call operating principles, works just like you know, our old days, our TV, okay, the tube TV, okay, something like that. If I can try to show you, okay, we have a, it will have a heating device lah, heating device, okay. It will have a heating device, and there will have one cathode. Heating device is sitting at the cathode, the negative, what we call the negative side. Cathode. And the positive is the anode. And they are all housed inside like a light bulb, right? Why? Because it has to be vacuum. Okay, inside it's all vacuum. No oxygen are allowed, because once you have oxygen go in, it will never work anymore. So it's in the vacuum condition. It's just like this one also vacuum. Okay, in the vacuum condition, what happened is that you need to have a power, okay, DC power, to actually heat up, okay, the heater, okay. It will heat up the cathode. And once the cathode material will heat up, right, the electron, okay, the electron will actually release from this cathode, okay, because it's a vacuum, so it will release in the vacuum. And then this is the plus, okay, this is the minus, okay. So the electron will actually move, okay, from the cathode to the anode, okay. So it will connect in so-called forward bias condition. So what if we put a negative here and a positive here, okay, and positive, right, have less electron, so that you are basically, you know, there is no conduction in between, okay. But when you put in this direction, it will have conduction, okay, you will have conduction. So in this way, it behaves, you know, like a diode that will allow current to flow in one direction but block in another direction. So this is how the old days valve, okay, working principle is. And of course, there are a few disadvantages, still big in size, okay. And the lifetime of this device are very short because it has a heating element. Okay, heating elements tend to blow off. I mean, it's just like our light bulb in the old days, right? From time to time. Okay, so when it blow off, you need to change the whole thing. All right. So this is how the old days, okay, when there is no diode, okay, these are the two types of what we call valve, okay, they use. Okay. Then, of course, what will be the modern application? Of course, nowadays, AC to DC converter, the two most we use is, of course, nowadays is the charger. Okay, of course, as we know that the USB or headphone charger is not AC to DC alone. Okay, because inside, after AC to DC, we still need to have a DC to DC to actually step it down or regulate the power they're going to charge our device. Okay, portable device or handphone. And then, of course, our EV chargers. Okay, this is definitely the future trend. Okay, and EV is basically run by battery. Okay, so battery is DC. So definitely, you will need to have a charger. Okay, that will convert AC to DC. So it depends on what type of charger you're using. Okay, the one that you see, this one is what we call a fast charger. Okay, fast charger means the moment you take this out and plug into your car, it's already DC. Okay, but our car, right, inside the EV car also have a what we call AC to DC converter. The difference is that one is slow charger because the current of power to charge the battery is lower. So the fast charger, again, it just depends on how much power you can deliver. Just like our handphone, right? Nowadays, we already go up to over 100 watts. Okay, so it can charge pretty fast. In the early 2000, right? Still when the Nokia phone are there, you know, we need to charge the phone for 8 hours. Okay, so every day before we sleep, put that in the charge, and next morning only it will be full charge. But nowadays, right, everything can be charged within 1 hour, okay, from 0 to 100%. So that is the advancements of all these power electronics. Because in the old days, the old handphone charger, right, still transformer based. Okay, that's why the power is low. Okay, so it require only 5 watts or less than that, okay, to charge your phone. Okay, now for rectifier, okay, rectification efficiency. So how to actually know how efficient? Okay, like I say, in the old days we use a motor. okay, or machine AC to DC machine, okay, so it's not that efficient. And then the new, what we call this uh, semiconductor one will actually improve its efficiency. So first of all, rectifications, okay, as we know that it's a process of converting the AC, okay, to DC. So efficiency, okay, even for power efficiency or rectification is the same. Okay, the output is what? The output is DC, right? So it's the output, okay, a DC power, okay, and the input is the AC. So this will be the efficiency. So how to calculate, okay, the output DC power is basically, you just measure the DC power lah. Okay, V, okay, DC and I DC. And the output AC power, okay, you just measure them in the form of RMS. Okay, you measure in the form of RMS means that you are measuring the AC. Both at the output, remember, both at the output. Okay. And I put a note here, okay, rectification efficiency is different from power conversion efficiency. So don't confuse these two. Okay. They look alike, but it's totally two different things. Power conversion means that if you have a power converter, okay, any converter, okay, you measure the power of input, and then you measure the power of output, regardless of AC or DC. So that's why power conversion efficient applicable to all four converters. So the efficiency, okay, of these converters is basically the power of output, okay, over the power of input. So that is what we call a power conversion efficiency. So these are the most common way and method that people use to measure lah, and tell you, oh, you see my power converter efficiency over like 90% and so forth. Okay, so back to rectification. Okay, rectification is both measure at the output, but we measure the entity is DC entity and AC entity. So we see how effective lah. Okay, in fact, it just try to, it's a measurement of ripple lah. That's why sometimes they say I rather measure the ripple factors. Okay, so ripple factors is in percentage. Okay, so you can see ripple factors, okay, is the VRMS over VDC. Okay, and then square minus 1 squared. All right, so ripple factor, or what we call rectification efficiency, is the indicator to see how good is your AC to DC conversion efficiency. Okay, not the power efficiency. Power, I say, the input power regardless of AC DC, yeah, output power regardless of AC DC. Okay, so these are the few ones that you should know. Okay, now we started off with a very fundamental or very basic types of what we call this rectifier. Okay, it's the half wave. Okay, half wave basically you just use one diode. Okay, and then connect to the load. What happened is that your input is sine wave AC, and the rectifier only allow the positive cycle to pass through. Okay, and blocking the negative cycle. Okay, so the cycle actually repeat lah. Okay, it's actually repeat. We don't see much application nowadays, especially those in power conversion. I mean, the reason is of course the power efficiency, conversion efficiency, as well as the ripple factor, are not that good. Okay, ripple factor are very, very high, and then conversion efficiency are very, very low. But still, okay, yeah, there are some equation to govern the operations. Okay, and then again, if you want to measure them in DC, okay, you basically take Vm. Okay, M is the peak. Okay, the peak multiplied by 0.31. And then of course the current will be divided by R, okay, the load resistance. Okay, so this is just V over R, okay, like Ohm's law. And for the RMS, which is the AC measurement, basically is going to be Vm divided by 2, okay, or okay 0.5 multiplied by your peak. And similarly, okay, for the I will be the V over R. So with that, you can actually calculate the VRMS, IRMS, right, and the VDC, IDC. So that you can actually, with all this, you can calculate the rectification efficiency, as well as the ripple factors, all right? It's, a simple, you can create this, okay, in MATLAB. Okay, these are the very old version I did already. Okay, you are actually measuring, okay, how we're going to measure in MATLAB. Okay, so of course we need to measure current, we need to measure voltage, and then for measuring the DC, right, we need to measure using the main blocks, which is the average block. And of course, we want to measure the AC, right? So we have to measure using the RMS blocks. So these two will measure the current, okay, and then of course these two will measure the voltage. You multiply them, okay, you get the power, then you will see, okay, the efficiency. Now, in terms of waveforms, okay, the waveform will look like that. Of course, we know that only the positive cycle can pass through, okay, and the negative cycle, okay, are blocked because it's only the half wave rectifier. Okay, let me see. I'm not sure I still have keep this or not. Half wave. Okay, I think I put in the old folders. Okay. Okay. Oh, I don't have this anymore. Okay, this is the one I have now. I didn't keep the old one. Anyway, it should show the operation because I started to change to use this diode. Okay, so okay, in this case, I just measure the voltage. Okay, in this case, I just measure the voltage and well, okay, so you can see only half wave pass through, but most importantly is the equation, right? Okay, so RMS, right, is basically divided by 2. Okay, it's divided by 2. So you can see that, the peak is 325, right? So divided by 2, okay, roughly is 161. Okay, so also remember the RMS, you have to set the frequencies to 50 Hertz. And then the average, okay, is multiplied by 0.38. Okay, multiplied by 0.38. So you will get roughly around 100 O2 ports, which will fit, okay, to the equations, okay, shows here lah. All right, 0.3 and 0.5. You will see that the RMS is slightly higher, okay, than this one. Where is my, go to the background already. Go to the background already. Okay. All right. So, okay, we move on to the full wave. Okay. Full wave is the one that the most commonly used up to today. Like I say, even our charger. Okay, our charger. You know, yeah, the first stage is always rectifier. All right. So it's still used up to today. So basically, yeah. It consists of 4 diode, okay, 4 diode, and then of course in this way that it will rectify it to DC with both positive and negative cycle. So and just bring it up, okay, to have this what we call both you know, cycles. Okay, we'll see it at the DC side. And then the equation to calculate RMS, okay, this is quite straightforward lah. Okay, 0.747 multiply by your peak. Okay, you get the RMS. Okay, and then divided by R, you get the current of RMS. Whereas for DC, okay, it's still slightly lower, okay, which is around 0.6366. Okay, multiply by the VM. Okay, and then okay, the current will be divided by R, which is dependent on your load here. Okay, so again, okay, this again the old one. The main difference you can see basically you will have both, you know, cycles, okay, on the positive. All right, and then let me see if I still have. This one or not this one. Rectifier. Try to find this. Full wave. Because I did 2 versions. These are all my very, very old files, which I didn't keep anymore. Okay, but it's quite easy to to create one. All right. If you are using the specialized power, maybe we will try to do one here. But I really don't keep it anymore. How come? I don't keep it inside. I don't have any copy of this. Okay. Okay, when we do this, you have a few options. Electricals. Okay, if we are using this power electronics, so you can use the universal bridge. Okay, the one that I'm using here. And then it's 3-phase, right? So we have to change to 2 arms. Okay, we change to 2 arms, we change to diode. Okay, then it just become a diode here. So this AC side is the DC side. And then we will pick up the AC source. Okay, you can take out the AC source. Of course, you can build it with the diode. It depends on, you know, types of experiment that you want to do. And we have, yeah, maybe you guys also can follow and try to do it, okay, together here. We will have a branch. We take the branch, okay, and then we will rotate it. Okay, we'll rotate it and double click. You just choose R. Okay, choose R. And then, okay, this one maybe we change to 3 to 5 hertz, which is our AC. And then we will need to have our sensor. We need both sensor, right? Current and voltage. Current and voltage. Okay. So we measure the current. And we measure the voltage. Okay. And okay, we have to measure current voltage. And now we need to measure both the AC and DC, right? So RMS. Okay, so to measure the, okay, make sure it's change to 50 hertz. Usually we just put it 0 for the initial value. And then we need to measure the DC, which is average. Okay, to measure the average, same. Okay, you need to change to 50 hertz. Okay, change to 50 hertz. So both of these are the voltage. Okay, and then you can also measure the current here. Okay, similarly, measure the current. Okay, then we go back to get the reading. Okay, get the reading. And you can put a scope, okay, to see the, yeah. And then maybe we run for 0.1 seconds. Okay. Yeah, I think that's all right. Just try and run. What happened? Oh, forgot to put the power GUI. So when you use a specialized power system, right, you have to put the power GUI, otherwise it won't run. Okay, so there will be the yeah, voltage and current. Okay, so it is the same because this is 1 ohm. All right, this is 1 ohm. Okay, of course, if you put 10 ohm, then you will just move 1 decimal. Okay, away lah. Okay, 1 decimal away. So this is the DC, this is the AC. Okay, of course, you can multiply them. Okay, you can actually multiply them to get the power, then you can actually calculate their efficiency. Okay, you can calculate their efficiency. Okay, so if we look at the waveform, okay, yeah, you should be able to get this waveform lah. Okay. All right, so yeah. If you want to use the electrical also can, okay, electrical, yeah, but you need to construct them using dial. I think they have a conversion block as well. The new one I got, old one don't have the new one I think it's here. Let's see. Yeah, they also have it actually. Okay, this is three phase. I think they got the three phase. Oh, they don't have single phase version. They don't have a single phase. But anyway, the principle is still the same. You just need to construct the diode. Okay, in order to do that lah. Okay, so that will give you some examples. Okay, let's keep this for a moment. Okay. All right, now we move on to three phase. Okay, three phase, I said you just add another arms. Okay, instead of 2 arms, now we just add another arm. So this is 1 arm, 2 arm, and 3 arms. Okay, and for three phase rectification, you will notice that still you will give all three phase, okay, to the positive side. So that's why it doesn't touches the 0. So it doesn't touches the 0 means that it will have a lower ripple factor. So we can see in three phase, right? It actually just take the outline of the peak. Okay, that will form this. So it does not go all the way down, touch 0 like this one. Okay, it's actually go all the way up and all the way down until it touches the 0 and then all the way up. So this will produce higher what we call ripple factors and also give you a slightly lower conversion efficiency. Okay, but of course this can be solved by adding filters. Okay, now we are not considering any filters. Okay, filter is just like additional stages to smooth it out. Okay, so when we talk about the pure rectification, right? But in the old days, right, when they didn't realize that filter can actually help up, right? This is what they did lah. Okay, so again, it will govern with the equation. Okay, the VDC is Vm multiplied by 1.654. Okay, and the VRMS is very close. You can see almost no difference. I would say Okay, this is 1.654. This is 1.6554. Okay. Yeah, almost no different. But in exam, please, yeah, you have to show me the difference in your exams. You don't put both until 1.65. If you put until this digit, right, it will be exactly the same. Okay, so what happened is exactly the same that you have 100% conversion efficiency, which is not true. So yeah, just to make sure that you differentiate the difference, okay, in terms of decimal number, okay, in your exams, okay, and okay, the average, okay, current calculation is slightly different, okay, is that when you calculate the IM, you need to multiply by 0.3183, okay. So these are the equation that you need to know. And here is the another examples, okay, showing the three-phase input, okay, and then show you the you can see that it is not touching the zero, okay, it's not touching the zero. So we can actually do that here again, okay. We just, oops, before that I need to disconnect this first. Okay. From here you just add another arms, one arm, two arm, three arm. Okay, apply, then you will just have three. Okay, then what we're going to do is just to create another two additional sources. Okay, and then three-phase sources here. And then all this will connect together. And then bear in mind, three-phase, right? So they will have in terms of angle, negative 120 degree. And this one is positive 120 degree. Okay. So the rest is the same. Okay. So when we run this, okay. So you see, see almost very close, right? The VDC and VRMS, right? 5, 3, 4. Okay, 534. All right, that's why it is multiplied by 1.6. Okay, it's multiplied the VM multiplied by 1.6554. So it's very, very just decimal point differences. And then when you look at the waveform, okay, you will see that it doesn't touches the zero. Oh, there's some fluctuation here. Never mind. But here you can see it's 400 over. Okay, if I change the scale, where is it? The minimum. Okay, if I change the minimum to 0, so you will see that, right? It's like the 0 is here, So the ripple is not as high as the 1. Okay, that compared to the full wave lah. Okay, a bit of this is because of solver problem. If you have a better solver, it should give you. You can see the resolution is not so high. Let me try changing the solver. still the same, not much better. Yeah, sometimes you have to play around with all this solver setting so that you will know which one is best, okay, for your simulation result. Still more or less the same. Okay, but never mind. Most important one is to know that it doesn't touch 0, and then it fits the theory equation that is stated in the textbook. That is the point. Okay. Yeah, the slide show different. I think this one, if I'm not mistaken, I simulate exactly follow the textbook, which is from the US wattage. From the US wattage, of peak, I think 170, so you get 200 over watt. So if we simulate based on Malaysia wattage, right? Malaysia wattage, the peak is 325, it's 325, so multiply by 1.6, yeah. So this is what we get lah. Okay, 500 over. Okay, all right, so we have all these three here already. Now we want to work out, all these half wave, full wave, and three-phase rectifier, and look at their efficiency, as well as their ripple factors. So you can see the first one here, it's actually divided by 3 parts, divided by 3 parts here. Okay, so the first one is the half wave, the half wave here. If we base on the power equation, we base on the power equation with 0.318 multiplied by big wattage square divided by R, right? So this actually P equal to V square over R. And then again, same for the BAC, this is a measure the AC, this is a measure the DC, which is the peak multiplied by 0.5 square over R. So yeah, when you divide them, right, you will basically cancel off the R. R is the log value. So that should be the same, because remember, rectification efficiency, we are measuring at the output voltage, and output current, which is flow into the same resistance value, which can be cancelled off when you divide PDC over BAC. So this is what you get. This is what you get. And then of course, both VM, also must be the same, right? So must be the same. So you will get around 40.5% of rectification efficiency. So very obvious, less than 50%, because we know that it only rectified half of the cycle only. Half of the cycle, so that you get around 40.5%. And then with that, yeah, this one actually you can cancel off both. And also with this one, you can calculate the ripple factors. So the ripple factor is actually go up to 157%, which is very high, and it is very obvious, in terms of this waveform. And now we move on to the full wave. Full wave, all right, again, in terms of 0.31 is double up, so it become 0.63, and this one 0.707, and equation are same. So this is just derived and show that, and you can see the efficiency double. Already go up to 81%. 81%. And ripple factor, okay, go down to 48%. Okay. And still is considered very high. Okay, 48% is really high. Simply because, like I said, the waveform, the rectified waveform, right, go all the way up and touches the zero and repeat. It touches the zero and repeat. Okay, so that, yeah, still considered high. Okay, of course, yeah, we know that it can be solved by a filtering process. And lastly, the three-phase. Okay, and the three-phase here, same lah. You just put in the equations, and you can see. Remember, with the two number very close on 1.654 and 1.6554. Remember this. Otherwise, you will get 100%. Okay, which is not true because this is already theoretical. Okay, so yeah, you will get the rectification of 99.83%. Okay, remember rectification efficiency and power conversion efficiency are two different things. And then when you use this to calculate the ripple factors, okay, you can see that it go all the way down to 4% only, which is less than 10%. Okay, of course, in the real one, we usually put it very low, some less than 1% and so forth. Just like in our DC-DC converter, remember we use like 2% or 1%. So with this one, okay, yeah. So you must know how to show all these equations that leading to determine, okay, the rectification efficiency, the ripple factors. Okay. All right. So up to this point, any questions? Hello? Any questions?
Sir?
Yes? I can't hear you guys.
No, sir.
Okay, thank you. Okay, so basically we done already first part of this. Okay, we move on. Okay, so the next one will be the controlled rectifier. Okay, the difference is that, okay, the diode we use, right, we provide only a fixed output voltage, right? Okay, we cannot control the voltage. So in order to control the voltage, right, it works, you require to use the thyristor. Okay, you require to use the thyristor. All right. The thyristor, as we already learned in the AC converters, okay, it helps to chop off the waveform, right? So that by doing that, okay, with the different firing angles, and then you can chop off the what we call this waveform, and then you can with that you can actually control, okay, the magnitude of the voltage. So that's why thyristors, right, sometimes they also call it SCR, silicon control rectifier. Okay, now this one is only applicable for controlling high power equipment. Okay, we almost, not say almost, I was very certain we no longer use SCR for low power application. Like our charger, we don't do that. You see, in our charger, right, even though we are using this AC to DC, right, we will have like roughly over 200 volt, but we use the DC-DC converter to step it down. Okay, we, of course, commercial one, we will use a flyback converter. Okay, with the help of high frequency transformer, we actually step down the wattage, okay, with insulation for safety purposes. So for high power, right, okay, they don't use DC-DC converter to step down. Instead, okay, they are using the thyristor, okay. So how it works? Okay, we look back at the half wave again. Instead of using a diode, we are using a thyristor. Okay, so again, you already know that thyristor, right? What they do, you firing at a different angle, you just chop it off, right? When you chop off one part of it, okay, that means the power delivered to the load is the power, the what we call the area under the graph. Okay, the area under the graph. So the VDC, okay, the VDC that is delivered to the load is governed by this equation, which will again include the cos alpha. Alpha is the firing angle. Okay, alpha is the firing angle. So it's Vm divided by 2 pi. Okay, Vm divided by 2 pi, and then multiply by 1 plus cos of your firing angle. Okay. So if we look at these simulations again, what happened is that this will be the output. Okay. So instead of showing the whole waveform, okay, but you can chop it off lah. Okay, you can chop it off, of course, and then you can measure. And of course, in this case, yeah, you can also measure the DC and AC. You will notice the efficiency will change. Okay, but for any load, right? Okay, we are usually look at the DC. You can see the wattage is going to be low. Okay, it's going to be low. All right. And then, okay, this is a firing angle. Okay, I think you all should know already when you all do AC. So this is pi divided by 2. Okay, so you can see it chop right in the middle of the half, wave lah. Of course, you decrease it, you will see the waveform. All right. Okay, so the same principle, okay, that applicable to full wave. The only difference is Vm divided by pi instead of 2 pi. Okay, because for this one, it's 2 pi. Okay, it's 2 pi. All right, because it's the whole cycle, including the one that is, you have to take account into this part where it's not rectifier. But for full wave, okay, because both also rectify already, so you only need to take account of the pi. Okay, 1 pi lah. Okay, so there's a difference. The rest is the same. The firing angle is also the same. Okay, the only difference is this one. Similarly, okay, as you can see that now we have both positive and a negative cycle here with rectified. Okay, so that you can chop off. Okay, you can chop off. Okay, so by doing that, okay, you can control the wattage, okay, that deliver to the load. Like I said, it's only for the high power equipment only. Remember, it's for high power equipment only. Low power, even our TV or printer, whatever house appliances, even your washing machine. I think washing machine nowadays already use the AC motor. Okay, refrigerator. I mean, most household thing we don't use this anymore. This one is only used for industrial equipment. Okay, big machine. Okay, industrial equipment. All right. Okay, so yeah, this is just the setting of these two. Okay, to do the firing angle. Okay, so now we will look at the, this one is very interesting example. Okay, as I said, right, this type of control usually apply for big, what we call this industrial equipment. Okay, industrial equipment. So industrial equipment are usually either a full resistive load, okay, or the inductive load. Okay, one of the industrial equipment, okay, use is the crane, okay, that will have a a magnet, okay, electromagnet used to suck the metal, okay, used to suck the metal, okay, to carry all these junk yacht thing. Okay, let me try to find a magnetic crane. I see. One of these example, but we don't really see it in Malaysia. This one, magnetic crane. Okay, these are all, magnetic crane. Okay, how strong you want the magnet to actually suck, right? You have to control. Okay, so it's high power stuff. Okay, so all these are magnetic crane. Okay, the high power stuff, that is where you can see the real, control rectifier being applied. Okay, so it depends on how much, this metal you want to suck out. You can control the strength of the electromagnet. Okay, so this is one of the application. So if you are applying this thing, right, to this, so as we know that electromagnet is made out of coin, okay, so it won't behave like a resistor. So it behave like, with the inductive, it's just treat it as inductive load, okay. So when you treat it as inductive load, right, so the VDC will behave, the equation will become like that. It's 2 Vm divided by pi and cos alpha. Okay, so it's very much different now. You can see, this one, resistive load, right? This is the equation. But inductive load, this is the equation. Why so? Because when you look at the waveform, okay, if I change this one to inductive load, you see the output, it will go all the way back. Remember at the inductive load, right? When it will reverse, okay, the polarity. So if it become like AC again, it become like AC again. Okay, the zero is here, go all the way down. Okay, so that is the reason why the M become multiplied by 2. Okay, it will become something like that. Okay, let me see. I got. Okay. Three-phase control. Okay, this is not three-phase, this is single phase. Yeah, that one has to be a single phase inductive. Wow, this is the, okay, try to find the old one I show here. Inductive load. Oh, okay, still here. Okay. Okay. Okay, so now you see what happened is that, you will end up with this problem. Okay, if you just connect it to, it's a problem. Okay, it's because rectifier, right? You're supposed to produce DC, but it's not DC. Okay, you have a negative. Okay, when you apply to all these, inductive load lah. Okay, to the inductive load, so you will have this issue. Okay, now the next questions. What is the solution? to this problem, because you know you apply to the magnetic crane, right? It's AC, right? So how you want to make it DC? Okay, the solution to make the inductive load behave like a resistor or resistive load in a control rectifier. Can anyone guess what would be the possible solutions? In fact, I already teach this one, you know, in our very first chapter, you know. The solution I already actually show it in our very first chapter lah. Not sure you all still remember it.
So add the capacitor, is it?
No, not at the capacitor. In our very first chapter, or
So is it to reverse the direction of current?
also no. Not at capacitor. Okay. Also not reverse direction. Try to recall back. I even show the example, you know, in the class. See, the problem is that we need to get rid of the negative thing, right? We need to, yeah, cancel off lah. In other words, the negative. Yeah, I don't put a solution here. Yes. All forgotten already. Wow, if this one final I come out, usually this one very low mark, don't worry lah. Usually it's 2 mark, okay, out of 20 lah, you know. Unless I ask you to draw it out lah, then I can make like, you know, 5 mark to 6 mark. No calculation involved, you know. Okay. Review answer. You all remember the flywheel diode? Still remember or not?
Yeah, sir.
The flywheel diode will help. You see the problem of this thing, right? The negative is because of the inductor. Okay, discharging, right? In the opposite direction. Okay, so in order to solve this problem, we use the flywheel diode. So what the flywheel diode did is that you just add a diode in parallel with this load. That's all you need, and then you run. And here we go. You see, beautiful, cantik. So that, you know, yeah, you control the magnet DC power firmly to hold, you know, the thing. Imagine if you have this negative, there's been the DC power applied to it, it's positive, negative, positive, negative. The magnet is the, you know, it will vibrate like in a sense. It will still suck. It will still suck, okay, because N and S will still attract matter. It doesn't really matter, but in fact, right, a lot of these metal junk, some of them will have magnetic properties. So when they have a magnetic properties, okay, then when you suck them up, right, if there are some, you know, NN, they will repel, right? So, or SS, they will repel, but you are running at a high frequency of this, you know, you will see it vibrate, and then you will hear the humming sound or something like that. Okay, so in order to solve this, okay, basically you just need to add this flywheel diode. Okay, sometimes it's so simple, you see it somewhere because you are not aware of it, of course you can't remember lah. So you can, this is like that, you just remove this one, then you know, you will solve this. Okay, so simple solution, right? You just put flywheel diode, you get 2 marks. Okay. Yeah, question like that are actually, again, I say it's just to make sure that, you know, student don't score too many high mark. Also, I got problem. I make it too easy, everyone score high. I make it too high, failure rate so high. So I will come up with this type of question that only a small group in the class or whoever pay extra attention to me will be able to answer. It's not tricky anyway, it's not like, I designed to fail you or no. Because first of all, I tell you the solution. I show you the example, but you think, this is not important, no need to really remember. Yeah. This is how the students lose their marks, but it won't really damage your CGPA it's just like slightly. Of course, if you are in the border of 80 marks, right, and you lost this, it becomes 78. Then I can't help. But those top students usually they end up with like 90 marks. 2 marks for them nothing. They say, sir, take it 2 marks, no problem. I still got 88. For those high CGPA student. But every student try to be aware of this Okay. Three phase already. I think we will stop here See, wait Three phase. Okay, still got 8 minutes. Cool. Can enough. Okay, but this one okay the flywheeling diode. Okay, to solve this issue. Okay, not just applicable to magnetic crane. Any inductive load any inductive load. Okay. Okay, the next one. Okay, the next one will be a three-phase control rectifier. Three-phase control rectifier, okay, sometimes we call it 6 pulse. Okay, sometimes we call it 6 pulse rectifier. Again, it is used in the industrial applications. Okay, industrial application usually like over 100 kilowatt. Okay, and then the firing angle usually they don't fire that much. Okay, they usually fire it from 0 maybe to 60 degree. Okay, 60 degree, and then because of there are 6 diode there, right? The 6 diode, each of them will have a what we call the gate. Okay, so that's why I call 6 pulse. All right, or 6 fs. Okay, the frequency okay, of the ripple voltage will be 6 times. Okay, so yeah, it's still the same. The only difference is we are replacing a diode with a thyristor. Okay, we are replacing a diode with a thyristor. Again, there are some basic equation that you need to know to calculate the average output voltage. Okay, which is the VDC. Okay, okay, it's a 3 square root of 3 Vm divided by pi, and then of course it's 3 phase, right? And then the firing angle. And then for RMS, okay, much more complicated. And I say the only thing that will change, right, is actually the alpha. The rest of it is fixed value. Of course, the VM, the VM, it depends on the magnitude of the input. Only these two are the variables, okay, and the rest is the fixed value. Okay, so these are some tutorial exercise. Okay, now, like I say, when you change the firing angle, right, you actually also changing the conversion rectification efficiency. So take from this example. Okay, this example is also from the textbook. Okay, so American voltage. Okay, 205, 10 ohm, firing angle of 60 degree. Okay, so again, it's more like the substituting the value, okay, of into the equation. You get the VDC, and you get the VAC, which is the VRMS. Okay, and of course, load value. Okay, divided by R, then you get the power of DC and the power of AC, and you will give the efficiency 77.8. See, without control, okay, without control, we get up to 90%, 99%. Okay, remember, because that our firing angle is 0. That's why you don't really cut off any portion, okay, of your waveform. Of course, you get 99%. But now remember the firing angle we set at 60 degrees. We literally cut off a bit of it. And with that will affect, okay, the rectification efficiency because it's no longer, you know, it's already cut off, right? Cut off. Okay. All right. Okay, this is just another examples. Okay. Yeah, to show the firing angles. I'm not sure I still keep this one. Wow, step the bridge. See, three-phase bridge. Thing. Okay. Okay. So these examples, okay, you cut it off with a 60 degree. I put 90, I believe I showed last time, right? Why? Yeah, we put 90 because of the 30 degree here, okay, minus whatever angle you need to minus 30 in order to get the actual, okay, firing angle because of here 30 degree because the three phase, right, is never start from zero here. The yellow is the first phase which will start at the angle of 30 degree. Okay, next. Oh, I think this one next class already. This DC motor already. Okay, okay, almost time already. Any questions? I need to sort out my team problem. Otherwise, it's going to be a big issue. No, okay. Okay. If no, I think we should be able to finish by next class or slightly, 30 over slide or 60 slide here. So we should be able to cover all this, you know, in time. Okay. And then, these are the example I have. When I run this, this will be the output lah. Okay, the shark fin output. Call it the shark fin output for the three-phase control rectifier. Of course, here I can reduce it to like 60. Okay. So 60 minus 30, so the actual firing angle is 30 degree. Let's see. Okay, you can see it goes slightly higher now. Okay, you control. Okay, how much is it? Okay, to go up and down. Okay. All right, so yeah, we're almost there already, almost done. The last part is, yeah. Okay, so this week is week 12, week 13. Okay, your assignment presentation, not presentation. There's no formal presentation, okay, for your assignment. It's only demo. Okay, just show me the demo of MATLAB and Plex will do lah. So I'm going to conduct the demo session on Monday, week 14. Okay, start from 3 o'clock. Okay, start from 3 o'clock. We have many groups, but if you get things done, run, and then you can just move on to, you know, I can just move on to the next group. Okay, I said, okay, your report, okay, make sure that, you know, do not have more than 3 persons. It can be 2 persons, or you want to do it alone, I have no objection. Okay. If you submit a report to me with 4 people names, okay, I will just divide the entire report marks by 2. Okay. So don't try to do that. I know some students will say, I don't care, just put my name. Then Dr. Rodney will just mark. So please be warned, okay, on this. If you try to just put 4 person, when I see 4 person name there, your mark automatically divided by 2. Because I assume that there are 2 groups, or 1 group with 2 person that were sharing the same piece of report. Okay, that is the reason behind why I need to divide the total mark by 2. That means the assignment is 30 mark in total. The maximum mark you can get is only 15. And some more those, if you are copy one, yeah, that means your maximum mark will be kept at 15. So you need to be much more hard working on your final exam. All right. Yeah, demo is pretty straightforward. Just make sure that we do it online. Make sure that your computer, your lab is running well. We can just confirm that, okay, the simulation is running consistent. Okay. All right. Okay. So, how to unshare the thing already? Wait. Okay. If no question, I think we can. Okay. Wait. Oh, finally, I find this. Okay. No question. I think we can end the class today. All right.